Welcome back to Calculus AB. This is Mr. Martha. So today we're going to be talking about different topics. The first one, 1.10, exploring types of discontinuities. 1.11, defining continuity at a point. 1.12, confirming continuity on an interval. And lastly, 1.13, removing discontinuity. So pretty much when a function means to be continuous, so that's what the main thing is about this topic, right? So what does it mean for me to have a function that's continuous? The simplest way that I can explain this is pretty much if you're drawing a graph, right? If you're drawing a graph and then you have to pick up your pencil, that means the function is automatically discontinuous, right? For you to continue the graph. But if you're always if you draw a continuous graph, right? If you don't have to pick up your pencil when you're drawing it across an interval, then we can assume that the function is continuous across that interval. So we have we use the limits to define continuity. And that's why it's so important in calculus, because once we can define continuity, we can start jumping into different things, like into derivatives and so forth, right? If this one of these conditions, if a function is discontinuous, for example, then we have to make sure that it might not be, might be able to apply more calculus to it, right? So let's look at the first one right here. So the first condition for a function to be continuous is pretty much that f of c is defined. The second condition is that the limit as x approaches c of f of x must exist. All right. And then the third one would be pretty much the limits as x approaches c of f of x is equal to f of c. All right. So if any of these three is not true, then the function itself is automatically discontinuous. All right. So I'm going to give you guys pretty much first one, like the first example right there. We see f of c is defined. So counterexample, when f of c is undefined, right? So we're approaching c from both sides, right? There is a limit there, but we do have a hole in the function, right? So you can think about that's like a little hole in the function. The counterexample. And then the second one would be pretty much like the limit doesn't exist, right? So if this is not true, if the second condition fails to exist, the function might be defined, like right here it's defined, right? But the limit doesn't exist because we're going in opposite directions pretty much when we're going from the right or the left side. And also, like, there might be an asymptote there, right? So again, in this case, there will be both, right? The function is not defined there, and the limit doesn't exist for 2b. All right, so that'll be the counterexample. And the last counterexample is that pretty much if they don't match, if this dot is not there, then it's not true. All right, so here we have a limit that exists, right? But it doesn't equal f of c. All right, the f of c is defined down here, right? So we have to be careful pretty much when we're talking about those three conditions. Again, if any of those three fail to exist, then pretty much we can assume that, well, not assume, but we can already say that the limit that the function is discontinuous. And then let's look at the next part right here. So here, right, so this was a question pretty much in the year 2011. It was one of the free response questions. So we're looking at let f be a function defined by f of x equals 1 minus 2 sine of x for x less than or equal to 0, and then e to the negative 4x for x greater than 0. So this is a piecewise function, right? So they want us to show that f is continuous at x equals 0. So again, pretty much if like it says right there, you may recall from college algebra or pre-calculus, discontinuities fall into two categories, right? Those two categories would be removable, and the other one would be non-removable. All right, so let's see if this function is continuous. So pretty much we know that f of 0, right, if we plug it in, it's going to go into the top function because that's the one that has the equals part. So we're looking at 1 minus 2 sine of 0, and that would be equal to 1 minus 2 sine of 0 again. That would be 0 again. So this is equal to positive 1. All right. And now we want to find the limits. So first condition, we found it, right? So condition number 1, f of c, which is in this case 0, is equal to 1. The second condition, let's see if it meets it, right? So we know it exists. Now let's find the limit. So the limit as x approaches 0 of 1. So we're going to be attacking it from the left side first. So that means this is a left side limit, and then this is a right side limit. So 1 minus sine of x, 2 sine of x, sorry about that. And that's going to be equal again. If you guys do direct substitution, we end up with positive 1. And then the limits, the second one, right, from the right side as x approaches 0 from the right side of 1 minus, well, I'm sorry, e to the negative 4 times 0. Right, so in this case, should be an x there first. We do direct substitution. We get e to the negative 4 times 0, which is e to the 0, which is just equal to 1. So pretty much, even though this is a piecewise function, both functions have the same value at 0. So we can say, therefore, the limit as x approaches 0 of f of x is equal to positive 1. All right. So we found that the second condition is true, that the limit exists, right? As x approaches 0 of f of x is equal to positive 1, so it exists. So we can check that one off. And then the last condition, we just have to check if both of these match. And then, so the limit as x approaches 0 of f of x must be equal to f of 0. So we can see that it's pretty much 1 on one side and then 1 on the other side. So we can say that this function is continuous. And then again, from discontinuities, like I said, they fall into two different ones, the removable and the non-removable discontinuities.